At the 2011 Nobel Prize ceremony, Adam Riess walked away having proven how the universe expands, the question that defined a century of cosmology. In 2024, he examined the newest James Webb data and said on the record that we may have misunderstood the universe. The man who won the Nobel for solving this is now saying the answer was wrong. This video is about what he found, what it means, and why the word being used in press releases is not the word Nobel laureates are using in conference rooms. The Hubble constant, h0, is supposed to be the one number that tells us how fast the universe is stretching apart. By definition, it connects the speed at which galaxies recede with their distance, in kilometers per second per megaparsec. For decades, cosmologists expected that no matter how you measured it, whether you looked deep into the ancient universe or surveyed the galaxies around us today, you would land on the same value within the margin of error. That is not what happened. Two independent strategies have been refined to measure h0. The first looks back to the universe's earliest light. The Planck satellite, mapping the cosmic microwave background, analyzes the afterglow of the Big Bang. Planck's approach is indirect. It fits a 6-parameter model called lambda, cold dark matter, to the ripples in this ancient radiation, using the physics of baryons, dark matter, and recombination to predict what the expansion rate should be today. The result is precise: 67.4 kilometers per second per megaparsec, with an uncertainty of 0.5. This is the early universe's prediction, resting on the assumption that the model itself is correct. The second approach builds a ladder, rung by rung, from our own Milky Way outward. The Riess team, led by Adam Riess, uses Cepheid variable stars, stellar beacons whose true brightness can be measured, to calibrate distances to nearby galaxies. Type Ia supernovae, exploding in those galaxies, extend the reach out to hundreds of millions of light-years. This is the distance ladder. Its latest result is 73.3 kilometers per second per megaparsec, with an uncertainty of 0.97. The ladder is anchored by geometric measurements, parallax in the Milky Way, masers in NGC 4258, and eclipsing binaries in the Magellanic Clouds. Each rung is cross-checked and recalibrated, but the answer stays the same. The expectation, rooted in the logic of physics, is that these two methods should agree. They are measuring the same universe, the same parameter, just from opposite ends of cosmic history. The difference between 67.4 and 73.3 is not a rounding error. It is a gulf that has only grown more pronounced as the measurements have become more precise. Both teams have published their methods, opened their data, and invited scrutiny. The numbers refuse to converge. The Hubble constant, once a symbol of scientific consensus, now stands as a rift at the heart of cosmology. The word tension suggests a minor disagreement, a statistical hiccup soon to be resolved. But the numbers now tell a different story. In physics, confidence is measured in sigma, standard deviations away from chance. 5 sigma is the gold standard, the line between anomaly and discovery. The Hubble constant gap has crossed that line. The odds of this being random are less than 1 in 3 million. In February 2024, the James Webb Space Telescope delivered a result that made even the most cautious cosmologists uneasy. Webb's infrared vision cut through the crowded star fields that once cast doubt on Hubble's measurements. The Riess team's new data, drawn from over 1,000 Cepheid variables in 5 galaxies, showed the same expansion rate as before. The agreement between Webb and Hubble's distance ladder reached 8 sigma, an 8 sigma confirmation. In everyday terms, that is a 1 in 1.6 quadrillion chance of error. The possibility of a fluke is gone. A 3-column error bar graphic now stands as a visual indictment. The Planck satellite's cosmic microwave background prediction sits on one side, its uncertainty band razor thin. The distance ladder, anchored by Cepheids and supernovae, stands on the other, equally precise but stubbornly higher. In the middle, the Webb confirmation overlays the ladder, its error bar shrinking further, leaving no room for overlap. The bands do not touch. The gulf is not closing. Adam Riess, speaking on the day of the JWST result, put it plainly. These JWST observations give us the most direct test yet of the crowding hypothesis. The near-infrared resolution of JWST shows that the HST Cepheids were not significantly biased, confirming the robustness of the local distance ladder. The data pipeline, the photometric models, and the artificial star tests all passed. The instruments were not broken. The data was right. What remains is the model. An 8 sigma discrepancy is not a technicality. In particle physics, it would trigger a paradigm shift. Here, it means the universe is not behaving as the standard model predicts. The phrase Hubble tension no longer fits. The numbers demand a new vocabulary, a recognition that something foundational may be wrong. The unease is no longer theoretical. It is written in the data, and it cannot be ignored. Astronomers once suspected that the distance ladder's biggest vulnerability lay in the crowded star fields of distant galaxies. In these dense regions, Hubble's detectors could not always separate one star's light from another's. If a Cepheid variable overlapped with faint neighbors, its measured brightness would be inflated, making the galaxy seem closer than it was. This effect, known as crowding bias, became the leading candidate for why the local expansion rate appeared so high. For years, critics argued that even the sharpest Hubble images, limited by a 0.05 arc-seconds pixel scale, could not fully resolve the tangle of stars in galaxies like NGC 4258 and GC 5468. The suspicion was that the distance ladder's foundation was compromised by invisible blending, and that a more powerful instrument might expose the flaw. The James Webb Space Telescope was designed to address this challenge head-on. Its near-infrared camera operates with a pixel scale of 0.031 arc-seconds, nearly twice as fine as Hubble's, and it observes in the near-infrared, where the effects of dust and crowding are reduced. Webb's observing campaign targeted 5 key galaxies: NGC 4258, NGC 5584, NGC 453, NGC 463, and NG54, each hosting hundreds of Cepheid variables. The team used a trio of filters, F09DOW, F1FW, and F200W, to capture the full range of Cepheid light, applying advanced point spread function fitting to deblend even the most tightly packed stars. Artificial star tests, numbering in the tens of thousands, quantified how much undetected blending could still slip through. The entire reduction pipeline was built to expose any residual bias, no matter how small. Before Webb, the crowding hypothesis stood as a plausible escape hatch, a way to explain away the tension as an artifact of flawed measurements. The arrival of a sharper, more sensitive telescope offered the first real opportunity to put this suspicion to rest. The stakes rested not on a single observation, but on whether the most advanced technology could find any evidence that the ladder was built on sand. The Webb telescope's deblending analysis delivered a final verdict that left no room for doubt. Using NIRCam's 0.031 arc-second pixel scale, the photometry pipeline stripped away the confusion of overlapping stars that once haunted Hubble's images. Every Cepheid variable in the SH0ES sample was re-examined, this time with the sharpest vision yet achieved in deep space. The process relied on simultaneous multiband point spread function fitting, using both theoretical models and empirical measurements drawn from isolated stars in each field. Artificial stars, 10,000 per galaxy, were injected into the raw data to test whether any hidden blending could survive the new scrutiny. The result? The average residual bias from crowding dropped to just 0.02 magnitudes, a level far below what could influence the Hubble constant. For most Cepheids, blended neighbors contributed less than 1% of the total flux. The main source of uncertainty shifted away from crowding and is now dominated by random measurement scatter and minor calibration terms. Independent teams ran their own pipelines on the same James Webb Space Telescope data, applying different algorithms and assumptions. Their distance measurements landed within 0.03 magnitudes of the SH-ES result. No group found evidence of a hidden flaw. The error budget, painstakingly decomposed, showed that the systematic error floor had fallen below the statistical noise. The artificial star tests, the cross-checks, the program IDs, and the public data releases all pointed to the same conclusion. The local distance ladder stands. The instruments were not to blame. The consensus, now anchored by an 8 sigma confirmation, forced the crisis out of the realm of technical debate. What remains is a problem that lives at the level of theory, culture, and the limits of scientific self-correction. Inside the conference rooms of the Kavli Institute for Theoretical Physics, the conversation turned raw. On October 23, 2019, during a session at the meeting called Frontiers of Cosmology, Adam Riess, a Nobel laureate and the architect of the distance ladder, put a pointed question to David Gross, another Nobel physicist whose career had been forged in the crucible of particle theory. The question was simple. How should the community describe the growing gap between the two measurements of the universe's expansion rate? Gross did not hesitate. He said, "I would call it a tension." Then he paused. "But honestly, it is more like a problem. And in particle physics, we would label such a situation a crisis." The word landed with weight in the room. Around them sat theorists and observers, some with decades invested in the standard cosmological model, others who had built their reputations on its predictions. A quick poll followed. Only a handful were willing to call it a crisis out loud. Most clung to the softer label, tension. The difference was not just semantics. In particle physics, a 5 sigma discrepancy is the threshold for declaring discovery or disaster. Here, that threshold had been crossed. The numbers were now separated by 8 sigma, a statistical gulf that left no room for comfort. Gross's candor exposed what official statements would not. In private, the language grew sharper, the anxiety more visible. The word crisis was spoken behind closed doors, while public reports urged patience and caution. The stakes were not lost on anyone in the room. If the gap could not be closed by new data or hidden error, then the problem ran deeper into the foundations of how the universe is modeled and understood. This was not the controlled uncertainty of normal science. It was the kind of problem that, if left unresolved, could unravel the story cosmologists have spent a century constructing. Official press releases from NASA and the European Space Agency have repeated the same word for years: tension. Every announcement, every summary of the Hubble constant gap returns to this term. Tension is a word designed to calm, not to alarm. It suggests a puzzle, not a threat. In the language of science communication, it signals that the problem is technical, temporary, and contained. The phrase appears in headline after headline: Hubble tension persists. James Webb. Space Telescope confirms Hubble tension remains unresolved. Nowhere in these statements is there mention of a crisis or a breakdown of the standard model. The public message is measured, almost routine. Inside the machinery of funding and peer review, the incentives run deeper. Grant applications and mission proposals are written to emphasize progress, not alarm. Calling the discrepancy a crisis could trigger special oversight, risk major projects, or threaten budgets for flagship observatories. The safest path is to cast the problem as a tension, an active area of research, a sign of healthy debate. Review panels are instructed to look for technical challenges, not paradigm failures. This is not a conspiracy, but a system defending its own continuity. The language chosen in official statements is not accidental. It maintains public confidence in ongoing missions like the James Webb Space Telescope, Roman, and Euclid. It reassures stakeholders that the scientific process is working as intended. But beneath the surface, the numbers are not converging. The error bars no longer overlap. The word tension is a shield, holding back the deeper admission that the universe may not fit the model that has guided decades of research. As the evidence accumulates, the gap between public reassurance and private alarm grows wider. The story continues with the options left on the table, each one demanding a sacrifice from the foundations of modern cosmology. 3 proposals now stand at the heart of the debate over the universe's expansion. Each promises a fix, but each brings its own complications. Early. Dark energy, the first contender, adds a fleeting field that surges about 380,000 years after the Big Bang. This brief injection of energy shrinks the sound horizon, the ruler set by the cosmic microwave background and measured by the Planck satellite. The smaller ruler pushes the predicted expansion rate higher, which seems to resolve the Hubble constant discrepancy. But the fix is rough. Early dark energy speeds up the growth of cosmic structure, deepening the S8 tension between observed and predicted galaxy clustering. Solving one problem, it stirs up another. A second approach asks if dark energy itself might evolve. The Dark Energy Spectroscopic Instrument, known as DESI, has detected hints that the equation of state parameter W could stray from the classic value of -1. If dark energy changes over time, the expansion history, distances, and ages across the cosmos must all be recalculated. The foundational assumption of an unchanging cosmological constant would fall. Yet DC's evidence alone cannot fully close the expansion gap, and shifting W risks new mismatches elsewhere in cosmology. The third proposal is to modify gravity. The Poincare gauge theory, developed at Cambridge, extends Einstein's equations with torsion fields that twist space-time itself. This alters the link between distance and redshift, letting expansion rates diverge without new energy. But rewriting gravity means rethinking every prediction from general relativity. Each fix patches one wound but unravels the standard model further. A higher Hubble constant does more than split the community, it rewrites the universe's biography. The standard model, with its slower expansion rate, stretches the timeline to 13.8 billion years. But if the local measurements are right and the universe expands faster, the cosmic clock loses nearly 1 billion years. Suddenly, the oldest stars, ancient globular clusters, some dated at 13.4 billion years, begin to outpace the universe itself. The margin for error shrinks to a knife's edge. The comfort of a cosmos older than its contents vanishes. Simulations that shape our understanding of galaxy formation and dark matter halos depend on these numbers. Codes like Illustris TNG and Eagle, tuned for a universe that grows slowly, now face recalibration. A faster expansion rate means galaxies form earlier and structures grow differently. The cosmic web, as mapped by decades of supercomputer runs, could be a mirage, built on parameters that no longer fit the data. Every prediction for how stars, galaxies, and clusters assemble comes under suspicion. The next test is already scheduled. The Euclid mission, launched by the European Space Agency, is set to deliver its first major results in 2026. Euclid will map the geometry of dark energy and the growth of structure with unprecedented precision, using weak lensing and baryon acoustic oscillations as independent rulers. Its findings will either deepen the crisis or force a new consensus. There is no guarantee that the numbers will converge. Adam Riess, reflecting on the latest results, put it simply: with measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe. The standard model, once a foundation, now feels like a scaffold with missing beams. The countdown to Euclid's verdict has begun. Until then, the universe waits, its true age, its fate, and even its origin suspended in uncertainty. Today, the world's most precise telescopes agree. The instruments were not broken, and the data is right. Nobel laureates now use the word crisis because the model, the very blueprint of modern cosmology, no longer fits the facts. This is not a technical error, it is the universe refusing to match our story. The abyss is not in our measurements, it is in our understanding. What if reality itself will not be softened?